Hello everyone. I again welcome you all in my next online class lecture 5. So today we'll begin our next topic on several types or classification of drawing. So before I start the today's class, so I'd like to revise the previous concept or previous classes which we already covered. So from beginning, if we see, we had a discussion of, we learned about moisture content. There is two way of representation of moisture: dry basis moisture and wet basis moisture. Wet basis moisture is the moisture of mass of moisture present in product, and in dry basis we have seen that there is a mass of moisture present in solid. And there is many different methods to determine the moisture content. So there are mainly two methods: direct method and indirect method. And then in direct method we have seen air oven method, vacuum oven method, ground oven fractional distillation method, and then infrared method. So all these methods, drying must be completed until and unless the two consecutive weighing of product become same. So you must remember, while drying a product, the two consecutive weighing should be same, then only you should stop drying. And then in indirect method, you have seen that calculating or focusing on some parameters which are related to moisture content. We calculate the moisture content indirectly, such as electrical resistance method, electrical conductance method, dielectric constant method, chemical method, such as so on and so forth. Then we have seen this equilibrium moisture content. So equilibrium moisture content means, suppose you keep a product outside an environment, then the moisture product may lose or product may gain some moisture from environment or to environment, depending on the vapor pressure gradient of water vapor present in product or atmosphere. So then after reaching to equilibrium, the moisture content of product will be known as equilibrium moisture content. And then we have seen the equilibrium moisture content versus equilibrium relative humidity graph. That curve is A-shaped curve, and that is called as Jobson isotherm. And then we have noticed different determining method for equilibrium moisture content, like static method and dynamic methods are there. Then we have seen different equilibrium moisture content models are there. Because why these models are necessary? Like if you want to calculate the value of equilibrium moisture content, or if you want to determine the equilibrium moisture content value, then without performing experiment, you can directly using the formula at that particular RH or at that particular temperature, we can generate the value of equilibrium moisture content of product. So there are several models are there, out of which Henderson equation is the most popular one. The formula is 1 minus RH equals to exponential of minus Ct me to the power n, whereas RH is relative humidity in decimal. C and N both are constant, depends on temperature. And then we have equilibrium moisture content Me in percentage dry basis, and then temperature T, absolute temperature in Kelvin. Yes. Then we have seen different methods of dryings are there, depending on the airflow and depending on airflow and grain flow. So if the airflow and grain flow both in same direction, then it is called as co-current flow. If the both occurs from opposite direction, then it is called as counter current flow. Another one, if the grain and the air both comes perpendicular to each other, then it is called as cross flow. So in cross flow, we have seen that the air temperature, means in all flows the air temperature remains constant, only the grain temperature change. And then we have seen the moisture content variation also in all these flows. And then we have seen this hysteresis effect Hysteresis effect means at a particular relative humidity, the value of desorption equilibrium moisture content and the value of adsorption equilibrium moisture content both are not same at same relative humidity. So in equilibrium moisture content versus equilibrium relative humidity curve, we have seen that the difference between desorption equilibrium moisture content and adsorption equilibrium moisture content is called as hysteresis effect at same relative humidity, must you mention. Okay, so up to this I think we have discussed. So if we proceed further, so here we have classification of drying. Okay, so based on grain flow and air flow, we have classified the drying process into two. One is three: co-current, counter current, and cross flow. Again, we can classify this drying process based on the thickness of the grain. Based on thickness of the grain inside drying chamber, we can classify the drying process into two processes. One is thin layer drying, one is deep bed drying. Thin and deep. So thin layer drying and deep bed drying. So these two we can classify based on the thickness of the grain present. So if the thickness of the grain is more than 20 centimeter or more than 20 to less than 40 centimeter, then it is classified into deep bed drying. And if the thickness of the grain inside the drying chamber is less than 20 or less than 15 centimeter, 15 centimeter, then it is called as thin layer drying. So here you can see, based on thickness of grain in drying chamber, drying is classified into two types. Thin layer drying, here you see thickness of grain is normally below 15 to 20 centimeter. All grain is fully exposed to drying air under constant drying condition, relative humidity and temperature. So if you analyze this statement, see in this thin layer drying, the thickness of the grain is very small, less than 15 centimeter. So in this case, we assume that the grain surface, all the grain surface are exposed to the drying air condition or air, temperature. So that's why the drying, becomes more perfect, or we need some less time to dry the product. So that's why it is said that all grain is fully exposed to drying air under constant drying condition, relative humidity and temperature. So complete exposure of grain to heated air, yes, because the thickness of the grain is very less. So here we can perform an equation. So we have the equation that is already we have explained. Moisture ratio equals to exponential of minus kT. So moisture ratio means we can write it as m minus me by m naught minus me. What is this m? M is the final moisture content after T time, whereas m naught is initial moisture content and me is equilibrium moisture content. And all these m naught, me, all these moisture content will be given in percentage decimal. Okay, in percentage, in percentage will be given in decimal and in dry basis. So the formula m minus me by m naught minus me equals to my exponential of minus kT, and this k is called as drying rate constant in unit second inverse. So in thin layer drying, we have seen that the thickness of the grain must be below 15 to 20 centimeter, and in thin layer drying the grain is fully exposed to air. Why? Because the grain thickness is so less, that's why the whole grain mass is can be exposed to the air. So that's why drying is very good in this thin layer drying. So now next we come to this deep bed drying. In this deep bed drying, the thickness of grain is more than 20 centimeter, as I said previously. And in this deep bed drying, you see one drying chamber has been given here. One diagram is given here. You see, from the bottom portion the air is coming, right? From bottom the air comes with the help of blower, and before it enters into the drying chamber, the air must be heated. So we use one heater. So first what we do, using the heater, the air must be heated, and that heated air is entered into the drying chamber with the help of blower. Now the drying chamber is filled with some grains, and the thickness of the grains is more than 20 centimeter and less than 40 centimeter. So that means the drying must be under deep bed drying. So now from bottom portion, if the grain first comes into contact with the heated air, that means that is the hot air, it comes into contact. So first the grain must, what will happen naturally? Naturally that portion or that lower portion of the grain will be heated so much. Whereas if you go little bit up, you will find the grain is not that much heated. And if you go more height, or if you go a bit more high, more top, then you will find that there is wet grain present. So this is the difference occurs in deep bed drying. So that's why this is non-uniform drying. This is not uniformly drying. This drying is not occurred uniformly. So bottom portion of the grain first, that is heated at a high rate, because the heated air comes into contact with the grain, comes into contact with the bottom portion of the grain. So there we get the dried grain. Now after this dried grain, if you go up, then the heated air, the hot air collects some moisture from the grain and becomes saturated. That means the temperature of the air now is going to be low. So that's why we found the drying zone, and after this drying zone, one interface is there, and that interface is called as drying front. So that interface is called as drying front. Now after this drying front, again if you go up, again if you go further, what happens? Again the air collects some moisture from the grain, and then the grain is losing moisture. Again the hot air collects the moisture. Again the temperature of air, it will go down, and the air becomes more saturated, more humidified. So that's why their wet grain is present. That's why the drying is not very much efficient at the top portion of the drying chamber. So there you see 16 to 20% of the moisture present in that wet grain. And after this, when the hot air exits the drying chamber, the air temperature, it goes down. And what about the humidity? Yes, humidity will be high or low? Yes, it will be high. It will be high. Why? Because the air is gaining the moisture from the product, and that's why the air humidity is raised, and while going out of the drying chamber, the air becomes more humidified, or the temperature of the air, it goes down. So this is all about your deep bed drying. So in deep bed drying, you can see one graph is plotted here, moisture content of product versus drying time. So you can see there 3 sections are there. One is bottom layer, one is intermediate layer, another one is top layer. So what is this bottom layer? So in bottom layer, you have seen that the drying is much more efficient, or the hot air temperature is very high. The temperature of hot air is high, or the air is not that much humidified. So that's why their drying is very efficient. That's why the moisture content present in the bottom layer should be very low, because drying is very sufficient. And if you go to the top layer, you see moisture content present will be very high compared to the bottom layer. Okay, so this is the difference. Now if we go deep bed drying, if you see here, drying takes place in the drying zone, and at entry point of the drying air, grain starts to dry, and drying zone is formed above the bottom layer, which comes in contact with the heated air, and then bulk of drying takes place in drying zone and moves along with drying air. So at air temperature is maintained at 43 degrees Celsius. For analysis of deep bed is formed with several thin layers. Air flow rate is less. the thin layer compared to the thin layer drying. So this is all about your deep bed drying process. So in thin layer drying, we have seen the grain thickness is very less, 15 to 20 centimeter maximum, and that's why in thin layer drying the grain thickness, or the thickness of the grain is less. That's why the grain is fully exposed to the ambient air. And in deep bed drying, we have seen that the thickness of the grain is very high, like 20 to 40 centimeter in the range, and that's why there is a section, top section, intermediate section, and bottom section. So in bottom section, dried grain are present. Why dried grain? Because that position the grain comes into contact with the hot air, and because of the hot air or less humidity air, the air collects more moisture. So that's why the air drying very much is, drying is very at high rate, or drying is very much sufficient in the bottom layer. And if you go further, you get the interface that is called drying front, and beyond drying front the wet grain is present. Why wet grain? Because at that time the drying air collects more moisture from the grain, and the drying air temperature also is gone down. So that's why in this particular top layer you find the wet grain of 14 to 16% moisture, and throughout the process we maintain the air temperature 43 degrees Celsius. Now there are some formulas. So we have seen that in thin layer drying the formula we use, that is called as MR, moisture ratio, equals to exponential of minus KT. Now for deep bed drying, here also we have to find out the drying time. So the formula you see, drying time is nothing but the time of advancement of drying front plus decreasing rate time. So what happens from bottom layer to you go up to the advancement with the drying front. So up to this to reach from bottom layer to drying front, the time requirement, that is the one section, plus next one decreasing rate time. So in that decreasing rate time, from drying front to the wet grain, slowly the drying rate reduces. So how much time it continues? So these both if we combine, then we get the deep bed drying time. So the formula of this time of advancement of drying front, you can say that time taken by the drying front to reach the top of the grain. So the formula is ms within bracket m1 minus mx divided by a into g within bracket hs minus h1 into 100. So what is this ms? ms is called as mass of dry solid. What is this m1? m1 is called as moisture at drying front. What is mx? mx is called as moisture at the exit of the drying chamber, means moisture of the grain at the exit of the drying chamber. So that will be higher or lower? Yes, that will be lower. Next, area is A, then drying rate, G is the flow rate of the dry air, and then HS is called as saturated humidity of air at the exit, because at exit the air becomes more saturated, and H1 is the humidity of inlet air, and humidity of inlet air will be much more less, because while entry point of the air, the humidity of air is very less. So that's why you call it as dehumidified air. So because while drying we send dehumidified air, and slowly while it comes out of the drying chamber, it becomes saturated, and that's why it is called as humidified air after drying. Next is decreasing rate time. So this decreasing rate time we can call it as rate decreases at the top of the drying chamber. As I mentioned that while it reaches beyond the drying front, then slowly drying rate reduces, because it collects more moisture from the grain, and the formula behind is 1 by k ln of within bracket mx minus me divided by m minus me. All the values of moisture content are given in decimal and in dry basis. So total drying time for this deep bed drying, we can write it as time of advancement of drying front, and then after drying front decreasing rate time. So this both if we combine, then we can say ms within bracket m1 minus mx divided by a into g within bracket h1 minus hs minus hm h1 into 100 plus 1 by k ln of within bracket mx minus me divided by m minus me. So now here you can see there are several drying models are available. So the concept is same. Why there's so many drying models are required? Because if we don't have the models, then we have to perform the experiments a number of times. So by using these models, by using these equations, we can directly calculate the predicted. So we can directly predict the moisture content of the product, that after t time the moisture content of apple could be this much, or after t time t2 time the moisture content of jamun will be this much. So we can predict the moisture by using the help taking the help of this drying model. So there are a number of experiments have been done till now. So I'll just give some model formula. You just try to remember it. Newton's model, moisture ratio mr equals to exponential minus kt. What is mr? Mr is m minus me by m naught minus me. This is called as moisture ratio. Then Page model, moisture ratio mr equals to exponential of minus kt to the power n. Then Henderson and Pavey's model, moisture ratio mr equals to a into exponential minus kt. Logarithmic model, Maynard, moisture ratio equals to a into exponential of minus kt plus c. And then two-term model, moisture ratio mr equals to a into exponential of minus kt plus b into exponential of minus k1t. Wang and Singh model, moisture ratio mr equals to 1 plus at plus bt square. And last one, modified Henderson and Pavey's model, mr moisture ratio equals to a into exponential minus kt plus b into exponential of minus gt and plus c into exponential of minus ht. So these all are my drying models. We can take any model and we can predict the moisture of the product after t amount of time. So here I would like to finish the today's class. So again, before I end this class, I would like to revise the topic. Yes. So today what we discussed then? First we have seen the different classification of drying. In our previous class we have classified into co-current, counter-current and cross-flow based on the grain flow and air flow. Now based on the thickness of the grain, we classify this drying into two: thin layer drying and deep bed drying. So thin layer drying means the thickness of the grain is less than 20 centimeter, and in deep bed drying thickness of the grain is more than 20 and less than 40 centimeter. And in thin layer drying the thickness of the grain is less. That's why the grain is fully exposed to the ambient air and the drying process continues very uniformly or very homogeneous. And in deep bed drying the thickness of the grain is more. That's why there are different sections and the grain drying also is not uniform. It's totally non-uniform. So what we have seen in deep bed drying, we send some hot air by using heater, and then hot air comes into the drying chamber with the help of blower, and while it enters into the drying chamber, it comes to the grain, comes contact with the grain, and the grain becomes dried and it loses moisture to the air, and then the air collects the moisture from a grain and the grain becomes dried in the bottom portion, and then that hot air again it comes goes to further top, and then it reaches to the drying front, and beyond drying front we see that there is decreasing rate occurs. Why? Because the grain collects so much air collects so much moisture from the grain, so that's why the grain air becomes almost saturated, and that's why the rate or drying rate is decreased. And there we have seen that 43 degrees Celsius temperature of air we generally maintain, and we have seen that this deep bed drying we analyze with the help of several numbers of thin layer. Okay, several number of thin layer drying. Okay, so that much up to we discussed, and then we have seen some formulas of this deep bed drying. We can calculate the deep bed drying time by these two combination of two. One is time required to reach drying front, another one is after drying front decreasing rate time. So these two if we combine we get the deep bed drying time formula. And we have seen there are several numbers of models are available, drying models like Henderson model, Pavey's model, Newton's model, Page model, modified Henderson and Pavey's model, logarithmic model. So this we discussed today. So now here I would like to finish this class. Okay, so thank you.